Hello students, sorry I can't be in class today. I thought I'd make a video to show you how today's lesson works. Today's lesson is again on heat transfer. This is for fire lesson 4. The difference in this lesson is we're going to look at the quantitative side of heat transfer. That is, we're going to put some math to it. So imagine you started with a 200 gram block at 80 degrees Celsius and a 100 gram block at 20 degrees Celsius, and you put those two in contact. Well, based on yesterday's lesson, you learned that the hot block that has very fast wiggling molecules would transfer some kinetic or thermal energy to the cold block where the molecules are wiggling slowly. The hot block molecules would slow down their wiggling, while the cold block molecules would speed up their wiggling, until eventually the two blocks were at the same temperature or thermal equilibrium. That is, the molecules in each block would be wiggling with the same kinetic energy. There's an equation that controls this. It's Q equals mCp delta T. So I forgot to mention now, if you look at these two, you might guess that the final temperature is halfway between the two. Halfway between 20 and 80 is 50. Or maybe you notice that this block is twice as big as this block. So the final temperature is going to be closer to 80 than to 50 in the middle because this block is bigger. So that's probably something you figured out while you were doing the warm-up activity for this lesson where you were mixing the hot and cold water. So let's try to figure out how to solve these problems. First, again, we're going to use this equation and look at this first. Q equals mCp delta T. So Q is the heat transferred, M is the mass, the Cp, or sometimes just C, is the specific heat, and the delta T is the change in temperature. The specific heat is a characteristic of a substance that tells us how much heat it takes to raise 1 gram of it 1 degree Celsius. Now, water has a specific heat of 1 calorie per gram degree Celsius. That means it takes 1 calorie of heat to raise 1 gram of water 1 degree Celsius. Now, that doesn't seem like a lot, just 1 calorie per gram degree Celsius, but it turns out that's a very high specific heat. Most substances have specific heats less than 1. Like iron has a specific heat of 0.107 calories per gram degree Celsius. So it takes about 10 times as much heat to raise 1 gram of water 1 degree Celsius as it does to raise 1 gram of iron 1 degree Celsius. So I'm going to help you with problem number 4, and you'll see that problem number 5, 6, and 7 on your worksheet work the same way. So Q, the heat, is equal to the mass times the specific heat times the temperature change. So in problem number 4, it asks if you heat 2 grams of water from 25 degrees Celsius to 26 degrees Celsius, how much heat was transferred to the water? Well, 2 grams of water, and there's your specific heat, times the temperature change, that is from 25 to 26 is a temperature change of 1. When we multiply all that out, we get 2 calories. The grams cancels, the degrees Celsius cancels, and that leaves us with the calories. So it takes 2 calories of heat to raise 2 grams of water 1 degree Celsius. Now keep in mind, as you're doing the other problems, there might be more mass and there might be more temperature change. So just plug those in accordingly and solve. This equation is going to help us understand what you did in the first part of the experiment. That is, how do you determine the final temperature when you're mixing 2 different quantities of a substance? Well, in the case of the blocks up above, they both had the same specific heat. So here's what this equation is telling us, that the heat lost from the hot block is equal to the heat gained by the cold block. So if the specific heats are the same, then really all that determines the final temperature is the mass and the temperature change of the hot block and the mass and temperature change of the cold block. So we're going to see this equation in action here in the next lesson, but basically this equation can now be boiled down to this equation right here. And it works something like this. If we want to find the final temperature of two quantities of the same substance, the example of above was maybe a block of metal. In your example today, you're using water, but you still have water's water, so the specific heat of water on both sides is the same. So really, all that determines the final temperature is the original masses and temperatures of what you're mixing. So it goes something like this. If you mixed 200 grams of water at 80 degrees Celsius, that's your mass 1 and your T1. If we add that to your mass 2 times your T2, that is 100 grams of water times 20 degrees Celsius of water, and then we divide by the total mass, 200 plus 100, that gives us 1,600 plus 2,000, divided by 300, and that's 60 degrees, the final temperature. And that's the same thing for these blocks up here. Whether it's water or blocks, if it's the same substance, we can make a prediction based on mass and temperature. Our prediction for 80 and 20 with 200 grams and 100 grams would be somewhere closer to 80 than to 20. If it was the same mass, then it would be right in between. And when we do the calculations down below, we can see that the final temperature would be 60 degrees. There you go.